So, a warm welcome to all of you to our next slot in our projective geometry class. We're still dealing with homogeneous coordinates, and this time we want to consider homogeneous coordinates over the real numbers. So, we will deal with the real projective plane. And if you remember our last slot, it started with the words, let K be a field, and from there we evolved in the following way, that we said we define a set P, a set L, which should play the roles of points and lines, and we defined an incidence relation such that for any field K, we got a projective plane. And just to recall the definitions, so the set P consisted of three-dimensional vectors over K, with taking the zero away from that set, and everything put into equivalence classes where we identify vectors modulo non-zero multiples. So point really is an equivalence class of vectors that point into the same direction. Similarly, we defined lines, so also they were an equivalent class of vectors pointing into the same direction. Each single line was one such equivalence class, and we defined incidence by the standard scalar product vanishing. We did that over arbitrary fields, and now we say, well, let K be R. So we now really deal with the real numbers, and in our equations here we replace every occurrence of K by the real numbers, and this slot will be all about the special things we get from the real numbers. And actually many of our next video lectures will focus on real aspects of projective planes. So let us take these three definitions as a reminder, and first let me motivate why we are doing that. So after all, we are mathematicians, and for mathematicians it's very often more desirable to have a theory over a general field than specializing down to the real numbers. But there are at least three reasons for considering the real numbers here. First of all, it's the space in which we are used to think, in which we are used to draw geometric pictures, and at least to understand the relation of pictures to our calculations. It's very very useful to have a clear understanding of the real projective plane. So it's something you can imagine, something that is concrete. With that comes something else. At least to a certain extent, the real numbers form a model of, the real world. So if we deal with structures in 3D, like for instance my model that I'm having here in the backgrounds, the vertices of that model, here are points in real 3 space, and the edges of that model are lines in real 3 space. So talking about the real numbers always refers to talking about, real objects. But there are also inner mathematical reasons for dealing with the real numbers. The real numbers have some special properties that are not common to all the other fields, and we will learn that some theorems about projective geometry hold only over the real numbers because of the special properties that we get from real numbers. We will come to that at one of the later video lectures. So, the main purpose of this lecture is to give you a kind of vivid imagination of how things happen in the real projective plane, and therefore we will, well, more or less take everything literally that we learned before and put it into the context of the real numbers. So we learned that a point is an equivalence class of vectors where we identify scalar multiples. So in our situation for the real numbers, now x, y, and z are real numbers. So we have a real three-dimensional vector pointing into some direction, and we consider the equivalence class of all the vectors pointing into the same direction, and we call this a point. Similarly, we call a line also a three-dimensional vectors, and I distinguish the variables. I take x, y, and z for the points coordinates, and a, b, and c for the line coordinates, and also here we identify scalar multiples. And then we have this incidence relation. So let me spell out what it means. So we had the standard scalar product, which, well, essentially over any field means that we take x times a plus y times b plus z times c, sum this thing up, and if this is 0, then we say that a point and a line are incidents. So in 3 space, this consists, so let this be somehow our R3, and let this be a point, so a representant of a point. So actually we could take any vector on that line, and let this be a line here, a representant of a line, and then we say, well, these two objects are incident to each other if they are really orthogonal in that space. We will see that this is an important point for the imagination for everything that will follow. I copied a picture of the projective geometry book here, which is kind of iconic for the situation. We have to think of the projective plane as well, the entire 3 space with these equivalence relations, and we may think of our drawing plane as embedded on a certain plane that does not pass through the origin of that plane. So I want to, well, make these things very concrete. So I want to develop what you just saw in that picture here for a moment. So I want to study the situation that a line is incident to 2 points. So in this picture here, you see you have, well, essentially 2 vectors, and the orange vectors here should represent points, and you have one blue vector which should represent a line. And in our picture, as I've drawn it here, you will recognize in a second, I will let these things move in a second, that you have orthogonal relations here. So this line here is incident to these 2 points, where I really now mean lines and points in a purely abstract manner. So if I say line, I mean an equivalence class of points of vectors, and if I say point, I mean an equivalence class of vectors here. And so let's just let these things move a little bit. So here you see that this blue arrow here is drawn in a direction that is orthogonal to the 2 other ones. Just to once more make it clear, for representing these points and lines of the projective plane, we could in principle have taken any other vector that lies on the span of those lines except for the 0 vector. So if we, instead of this point here had taken this vector, then that would really represent the same point, and we're really talking about orthogonality between linear subspaces. So in that picture you see that the space spanned by the blue vector is orthogonal to the spaces spanned by the two orange vectors. So how does this fit into, so we're speaking usually about the projective plane and not about the projective space, and here everything looks so spatial. So where is our plane actually sitting? And let me give you another picture of what we have here. So the idea is to intersect the image that you have here with a certain plane, and we will see that now. Let me first think, what is the plane we are talking about? And actually there are many choices, and one of those choices will be taken very often. The one of the natural choices is to say we put everything on a z equals 1 plane, and well, essentially we identify points in R3, so this in R2, so this one here should be a point in R2 with our projective embeddings via this map here, that we say, okay, for a certain point xy, we consider the three-dimensional vector of x and y taken to the z equals 1 plane, and then we take the equivalence class of that. And this is called the standard embedding. There are also infinitely many other embeddings by choosing other planes on which the points lie. But this here is particularly convenient. And if we do so, our equation here becomes essentially x times a, y times b, plus 1 times c, which is an implicit form of a line in the usual R2 plane. So we see that these vectors here can be considered as lines in R2, and let me now show you a picture of that situation. So here you see a picture of that situation. I included the z equals 1 plane in the picture. I intersected our vectors here with the z equals 1 plane, resulting in these 2 points. So these are the 2 points that come from the standard embedding. And we have our line here being incident to these points, which now means if we consider the parameters a, b, and c as the parameters of this line in our real space, that this vector here really represents this line in our drawing plane. So after all, we see that this interpretation of points and lines both as vectors via the interpretation that this vector here is a normal vector of a plane spanned by that line and the zero vector, right away translates in the situation that this line here is the join of these 2 points. So we see we get well, a really reasonable understanding of how our usual drawing situation embeds in the projective setup. Here comes another picture. Here you see the situation where you calculate the intersection of 2 lines. And here I intentionally used 2 different colors for the line. So you have a cyan one, and the corresponding vector is here, and you have a blue one, and the corresponding vector is here. You see that those 2 vectors are normal vectors to the planes spanned by the zero vectors and the corresponding lines. And you see, well, if a point is on both lines at the same time, it must be normal to both of those vectors. So you see, the meet of the line is essentially the same as the same kind of calculation. You're looking for this time an orange vector being perpendicular to both vectors simultaneously. So when I'm talking about this plane here and talking about those embeddings here, you see I will not get all the points of the projective plane. So what I will essentially get is only those points that correspond to equivalence classes that have a non-zero entry in the last spot. So whenever you take a point from your R2 plane embedded that way, you end up with a vector that has a non-zero entry in the last coordinate, essentially saying that you don't get all of them. We call those points in the standard embedding finite points, and there are also infinite points, and these are those that have a zero in the last entry. You will in a minute see that those points correspond to vectors that lie in the xz plane and essentially intersect this line, this plane here, infinitely far away. And all those points will lie on a common line. And what is the coordinate of this common line? Well, it's actually the line that points in the direction of this axis here. So this is a normal vector, and this normal vector is orthogonal to the xy plane, and this represents all the points that simultaneously lie at infinity. I want to remind you that at the very beginning of our projective geometry class, I showed you that there is this nice model of extending our usual drawing plane by points at infinity in any direction and putting all those points on a line. Now we have a model for that. This, what we see here, is actually one concrete representation of the structure we were talking about abstractly. So I now want to, well, switch to a more interactive mode here, and I want to show you well, how this situation essentially behaves if I start to move the points. Let me first explain what I did here. So let me look just horizontally on the whole thing. Here you see the situation of the drawing plane, of the R2 plane essentially, and we have four little white points. These are these four little white points. They correspond to those four little white points. Here we calculate the two lines that join these points and calculate the point of intersection of these two lines. So you see how this picture here literally corresponds to the one you have here. And now let's do a few experiments. So let's first say move our lines a little, and you see how everything behaves nicely. And now let's do the following experiment. Let's rotate this little white point here around the other one and see what happens. So our orange point moves very far out and comes back from the other direction, and this essentially corresponds to passing through infinity. And now let me just try to adjust it in a way that it really closely matches the infinite situation. There you see our point lies almost, So you see the orange vector here, and this orange vector lies almost in the xy plane, so telling you that it intersects these two lines here very, very, very far out. This concludes our first part of talking about the real projective plane. In the next slot, we will talk about join and meet in the specific situation of the real projective plane.